Page 50. This is our first lesson in our study of pressure. After pressure, we'll study flow. And most of what we learn regarding pressure will be directly applied in the unit on flow. It's absolutely essential that we are familiar with and able to interconvert various physical units. The units we'll be looking at specifically are these. So there are several systems in use. In the SI system, meter is the fundamental unit of length, kilogram the unit of mass, second for time, and newtons for force. And CGS system is commonly used in laboratory, and the unit of length is a centimeter, for mass it's a gram, for time it's seconds, and for force the unit is dynes. In the British system, the unit of length is a foot. The unit of mass is either a slug or a pound mass. Time is a second, and the unit of force is pounds force. It's interesting that in the British system we have both pounds mass and pounds force. I'll be primarily using the unit of slugs for mass. So you'll have studied most of these, well, all of these in physics, but let's spend a few minutes reviewing. It's just so important. So mass is the amount of matter in an object. As I mentioned, in the SI unit it's kilograms, in the British units it's slugs, and in the CGS system the unit is grams. And as long as the amount of matter remains the same, its mass is constant. Weight, symbol is W, is the force of gravity on an object. In the SI unit it's newtons, in the British unit it's pounds, and in the CGS system the unit is dynes, D-Y-N-E, or D-Y-N for short. Consider an object with a 1 kilogram mass. A newton of force is defined as that which would cause a 1 kilogram mass to accelerate at 1 meter per second squared. The force of gravity on the surface of the planet is relatively constant, and therefore we have a term entitled the gravitational constant, which attracts a 1 kilogram mass with a force of 9.8 newtons. And therefore the weight of a 1 kilogram mass is 9.8 newtons. The force of gravity will cause any object to fall and accelerate at a rate of 9.8 meters per second squared, or 32.2 feet per second squared. In the British system, the unit of force is a pound, so pound force will cause a mass of 1 slug. And a slug is a relatively large mass, as we'll see. It'll cause a mass of 1 slug to accelerate at 1 foot per second squared. The force of gravity on planet Earth is 32 pounds per slug of mass, and so 1 slug weighs 32.2 pounds. And the force of gravity will cause an object to accelerate towards Earth at 9.8 meters per second squared and 32.2 feet per second squared. In the CGS system, the unit of force is a dyne, and 1 dyne will cause a 1 gram mass, and that's a very small mass, to accelerate at 981 centimeters per second squared. So the force of gravity on any object is 981 dynes per gram of mass. So the weight of a 1 gram mass is 981 dynes. Acceleration due to gravity is 981 centimeters per second squared, which is 9.81 meters per second squared, or 32.2 feet per second squared. On the bottom of page 50 we have some units and some conversions between them. For the most part you're not expected to memorize these units, but you would be expected to be able to interconvert. That's vitally important. So there may be the odd unit you have to derive from other basic metric units. You must learn the metric units, the multipliers. Since a newton is the force that would accelerate a kilogram mass at 1 meter per second squared, thus the units of a newton are kilogram meter per second squared. And since a pound force causes a 1 slug mass to accelerate at 1 foot per second squared, thus the unit of pound is a slug foot per second squared. And since a dying force will cause a 1 gram mass to accelerate at 1 centimeter per second squared, the unit of dying is a gram times centimeter per second squared. Some force-to-force conversions. A pound is 4.448 newtons. So a newton is a relatively small force, and a newton is 10 to the 5 dynes, and so dynes are a really small force. Actually, I'd like us to convert right now, get some practice with that. Let's convert, and how many dynes is 1 newton? Well, a dyne is defined as a gram times centimeter per second squared, and a newton is a kilogram times meter per second squared. So we can convert kilograms to grams and meters to centimeters, and that should do it for us. We'll need 2 conversion factors. I'm going to cancel out kilograms, go to grams, and we're going to cancel out meters and go to centimeters. And we should wind up with grams times centimeters per second squared, or dynes. Right, so we know that there's 1,000 grams in a kilogram and 100 centimeters in a meter. So we have 10 to the 5 grams centimeters per second squared, or 10 to the 5 dynes in 1 newton. And I do that calculation with you because we'll need to do it from time to time in this unit. Mass-to-mass conversions. A slug is 14.59 kilograms, so it's quite a hefty mass. And a kilogram is 1,000 grams. Now a gram is approximately the weight of a raisin. Helpful to keep that in mind. Mass-to-weight relationships. A kilogram weighs 9.807 newtons, owing to the gravitational constant. A kilogram weighs 2.2046 pounds. And a slug mass weighs 32.17 pounds. And 453.6 grams is a pound. And since a gram weighs 980.7 dynes, therefore a kilogram would weigh 980,700 dynes. We'll be using these from time to time. Let's look at page 51. Density. There are actually 2 kinds of density. We have mass density and weight density. And mass density uses the symbol, this letter, Greek letter. It's the Greek letter rho. Looks like a P in English. And it has units of mass per volume. So rho is mass over volume. We'd have units of kilograms per cubic meter in the SI system, grams per cubic centimeter in the CGS system, or slugs per cubic foot in the British system. We also have a unit called weight density, which commonly uses the symbol capital D. And this is actually weight per unit volume. It'll have the formula D is W over V. In the SI system, the units will be newtons per cubic meter. In the British system, we have pounds per cubic foot. In the CGS system, we'd see dynes per cubic centimeter. Note that since weight density is written as weight over volume, and weight is written as mass times the gravitational acceleration, we'll have, therefore, weight density is mg over v. And since mass over volume is mass density, rho, therefore we have weight density is mass density times the gravitational constant. D equals rho times g is a conversion that we will use from time to time. I want us to get familiar with some of these conversions, so it's worthwhile spending the time doing these interconversions. These are 3 standard substances, water, mercury, and air, and I'd like for us to calculate the density of water, mercury, and air in the variety of units that we've just discussed, both in weight density and in mass density. Now, once we've done it for water, the rest will be extremely simple, as you'll see. It'll take just a minute. Let's go through the density calculations or conversions for water. So how many kilograms per cubic meter is equal to 1 gram per cubic centimeter? How many kilograms per cubic meter is equal to 1 gram per cubic centimeter? So we'll need to convert from grams to kilograms and cubic centimeters to cubic meters. There are 1,000 grams in a kilogram, and we cancel out per cubic centimeters and go to per cubic meters. What's the conversion? We know that 1 meter is equal to 100 centimeters, and if we cube both sides of this, we'll have 1 cubic meter is equal to 10 to the 6th or a million cubic centimeters. So 10 to the 6 cubic centimeters is a cubic meter. We're multiplying by 10 to the 6 and dividing by 10 to the 3, so we'll get 10 to the 3 kilograms per cubic meter is equal to 1 gram per cubic centimeter. Many times in the lab you are asked to bring the density of a substance to know what part of the SEP funnel it's in, the bottom or the top, and many times students bring me units of kilograms per cubic meter, and I ask them, will that be on the top or the bottom, will it sink or float, and many times they don't know. But if we work in grams per cubic centimeter and you know that water has a density of 1, it's relatively easy, so convert them to grams per cubic centimeters for the organic lab. Next we have how many grams per liter is 1 gram per cubic centimeter. All we have to do is convert from cubic centimeters to liters, and a cubic centimeter is identically the same as a milliliter. So simply a factor of 1,000. There are 1,000 cubic centimeters or milliliters in a liter. So that's 1,000 grams per liter is the mass density of water. Our next one is how many dynes per cubic centimeter are equivalent to 1 gram per cubic centimeter. So we're going from mass density to weight density. We need to convert from grams to dynes. And do you recall that the force of gravity is 980.7 dynes per gram of mass. So therefore, the mass density of water, 1 gram per cubic centimeter, is equal to 980.7 dynes per cubic centimeter as a weight density in the CGS system. All right, let's get the weight density of water in newtons per cubic meter, which is the SI unit of weight density. But since we've just got the weight density of water in the CGS system, dynes per cubic centimeter, probably easier to convert from there. So 980.7 dynes per cubic centimeter. We'll convert from dynes to newtons and cubic centimeters to cubic meters. A short time ago we converted between newtons and dynes. Do you recall there were 10 to the 5 dynes per newton? And we also recently converted from cubic centimeters to cubic meters. There were 10 to the 6 cubic centimeters per cubic meter. So we can write this as 10 to the 5 dynes per newton. And we can cancel out per cubic centimeters and go to per cubic meter. There are 10 to the 6th cubic centimeters in a meter. So we're multiplying by 10, so that comes out to be 9807 newtons per cubic meter is the weight density of water in the SI system. Large number. Let's go to the British system. What's the weight density of water in pounds per cubic foot? And since we have it in the SI system, I think it'll be easiest to convert from there. 9807 newtons per cubic meter. So from newtons to pounds and cubic meters to cubic feet. Now newtons to pound was given at the bottom of page 51. Let's take a look. Here we have 1 pound is 4.448 newtons. All right, so a pound is 4.448 newtons. All right, so we're going to cancel out newtons and go to pounds. So 1 pound is 4.448 newtons. And then we want to go from cubic feet to cubic meters. I want to cancel out per cubic meters and go to per cubic feet. Now what is that? Well, 1 meter is 3.28083 feet. Now where does that come from? Well, I'll give it to you here. 1 meter is 3.28083 feet. And of course you don't have to remember that conversion. I'll give it to you anytime. But we need to go from cubic meters to cubic feet. So if we cube both sides, you'll find 1 cubic meter is equal to 35.31 cubic feet. 35.31 cubic feet per meter. That's at least approximately correct. And if you work this out exactly, it comes out to 62.43 pounds per cubic foot. That is the weight density of water in the British system. And finally, let's calculate it as mass density of water in the British system, which is slugs per cubic foot. Since we already have it in the weight density as 62.43 pounds per cubic foot, we could just convert from pounds to slugs. So back to page 50. 1 slug is 32.17 pounds. 32.17. So that'll be slugs per pound, 32.17 pounds per slug. If you work that out exactly, I believe it is 1.9403 slugs per cubic foot, and that is the mass density of water in the British system. So let's quickly recap here. A gram per cubic centimeter mass density of water in the CGS system, equivalent to 1,000 kilograms per cubic meter mass density of water in the SI system. In the lab, we often use 1,000 grams per liter. 980.7 dynes per cubic centimeter is weight density in the CGS system. 9807 newtons per cubic meter is weight density in the SI system. 62.43 pounds per cubic foot is weight density in the British system. 1.9403 slugs per cubic foot is mass density in the British system. Right, so let's fill in this table on the left-hand side here on page 51. This may seem redundant, but it's so important that you are familiar with these units. I believe it's well worth the time to do this. So, mass density of water, 1 gram per cubic centimeter. 1,000 kilograms per cubic meter. In the lab, we'd say 1,000 grams per liter. It was 980.7 dynes per cubic centimeter. 9807 newtons per cubic meter. 62.43 pounds per cubic foot. 1.9403 slugs per cubic foot. Now, I started off with a density of water of 1 gram per cubic centimeter. You should be aware that's only true at a certain temperature. Here's a plot of the density of water versus temperature. Notice at higher temperatures the density decreases, as true for all liquids. If you focus in on the low temperature zone here, you'll actually notice that there is a maxima at exactly 3.98 degrees C, or we can say 4 degrees C. The density of water is actually 1. And that's the term we're using. We refer to water with a density of 1 gram per cubic centimeter, but you need to understand that that's at 4 degrees C. At room temperature it would be less, and we'll cover that later. It's 0.9982. We'll use the density of water at different temperatures in some of our labs. Let's digress for just a second and talk about specific gravity. Sg is defined as the mass of a substance divided by the mass of an equal volume of water. So in the case of water, if we're dividing the mass of water by the mass of water, then of course the specific gravity of water will in fact be 1. It's kind of neat that in the CGS system, the density of water is numerically the same as its specific gravity. Now, mercury is 13.596 times denser than water. It has a specific gravity of 13.596. So if you wanted to calculate the density of mercury in any of these units, you simply multiply each of these values by 13.596. For example, the mass density of mercury in the SI system would be 13,596 kilograms per cubic meter, and so on. Now, the density of air is 0.00129 grams per cubic centimeter. Now that's subject to both temperature and pressure considerations, and this is true at STP, 0 degrees Celsius and 1 atmosphere pressure. If we want to calculate the density of air in any other unit, you'd multiply by these factors. For example, in the SI system, the mass density of air would be 00129 times 1,000, or 1.29 kilograms per cubic meter, or 1.29 grams per liter, and so on. Let's take a look at page 52. We've made mention of the gravitational constant. That is the constant acceleration due to gravity. We've been using the value 9.807 meters per second squared. Turns out it's not quite as constant as one might think. It is a function of latitude, which is the north-south position on the surface of the planet, as well as the altitude of an object. In terms of latitude, turns out the Earth is not a perfect sphere, but somewhat flattened at the poles, and therefore its gravitational acceleration is not constant everywhere at sea level. At various latitudes it's different. There's an equation given here for calculating the acceleration due to gravity at various latitudes, and if you work that out at sea level, at the 42nd parallel, north latitude, Windsor, Rome, Italy, is 9.8035 meters per second squared. What about altitude? The greater the distance between two objects, the less the force of gravitational attraction between them. So objects that are at higher altitudes above sea level will experience less force of gravity than objects at sea level. There's an equation for calculating acceleration due to gravity at various altitudes. Turns out at Windsor, Ontario, which is 581 feet or 177 meters above sea level, the acceleration due to gravity is calculated to be 9.8029 meters per second squared. So, notwithstanding or regardless of these foregoing calculations, we will use the standard value for g, which is 9.80665 meters per second squared, and rounding to 4 sig figs, that's 9.807 meters per second squared, or 32.17 feet per second squared, or 9.807 newtons per kilogram, or 32.17 pounds per slug, and will experience no difference except perhaps in the fourth decimal place, which has no bearing at all on most of our calculations. Please take a look at page 54. On page 54 we have a definition of specific gravity. We touched on it earlier. It's the weight of a given volume of a substance divided by the weight of an equal volume of water. It can be calculated as the weight density of a substance divided by the weight density of water, or the mass density of a substance divided by the mass density of water. And again, we make the assumption that we're talking about water at 4 degrees C, where its mass density is 1 gram per cubic centimeter. Note that for specific gravity, all units of density will cancel, so specific gravity has no units. The weight density of water is 1 gram per cubic centimeter. The specific gravity of water is 1. The weight density of mercury is 13.6 grams per cubic centimeter, and the specific gravity of mercury is 13.6. It's convenient for those of us who work in the lab that specific gravity is numerically the same as weight density if you work in the CGS system. And this is not true in other systems of density. For example, in the SI system, the density of mercury is 13,600 kilograms per cubic meter, and that is numerically different than the specific gravity. This definition of specific gravity, the weight of a given volume of substance divided by the weight of an equal volume of water, it's applicable to solids and liquids, but it's not applicable to gases. So what about gases? Well, gases are much less dense than solids and liquids, so they're treated differently. Density of gases is usually reported in units of grams per liter rather than grams per milliliter or grams per cubic centimeter. For example, chlorine gas has a density of 3.17 grams per liter. Air is 1.29 grams per liter at STP. So the specific gravity of a gas is calculated as the ratio of the density of the gas divided by the density of air at STP. So you're dividing by 1.29 grams per liter. In the case of chlorine, that would be 3.17 grams per liter divided by 1.29 grams per liter, or 2.46 is the specific gravity of chlorine. Let's give this a try. Carbon dioxide has a specific gravity, or relative vapor density, of 1.53 at STP. So this term relative vapor density is often encountered in occupational health and safety literature. It simply means the ratio of the density of a gas compared to that of air, the relative vapor density. So it's synonymous with specific gravity. So for carbon dioxide with a relative vapor density of 1.53 at STP, let's calculate its density. All right, so here I have the density of CO2 will be its specific gravity times the density of air. So that'll be 1.53 times 1.29 grams per liter, and you always use air at STP. And that's 1.97 grams per liter. So CO2 is almost exactly 2 times the density of air. Hydrogen, the lightest gas, has a density of 0.089 grams per liter. What's its relative vapor density? In other words, what's its specific gravity? We'll just take a ratio of the densities. So the specific gravity of hydrogen will be its density, 0.089 grams per liter, divided by the density of air, 1.29 grams per liter. Units cancel, and that comes out to be 0.069. So as a relative vapor density, what is that if I take the inverse, 1 over 0.069? Turns out to be about 14.5. We can say that air is 14 times denser than hydrogen, or hydrogen is 14.5 times less dense than air. Please take a look at page 55. Page 55, we'll finally get to calculate pressure. So a fluid at rest exerts a force and a pressure on the walls of its container. The force is perpendicular to the walls of the container. So here's a cylinder filled with a liquid. It's got holes at 3 different levels, 3 different heights of liquid, 3 different depths of liquid. And the deeper the hole is, the deeper the liquid, the greater is the pressure, as evidenced by the fact that the liquid travels farther from the lower hole. So pressure is calculated as force per unit area. And in the SI system, it have units of newtons per square meter, which is defined as a Pascal. In the British system, that'll be pounds per square foot, PSF, or even more commonly, pounds per square inch, PSI. In the CGS system, that's dynes per square centimeter. These are units of pressure. Now, the volume of liquid in a container can be calculated as area times height, right? For example, square meters times meters would be cubic meters. A times H. Now the area, if the container is round, the area can be calculated as pi r squared. We'll most commonly encounter the equation pi d squared over 4. Do you know where that comes from? So if you have pi r squared is the area of a circle, we can write the radius as the diameter divided by 2, and then square that. That'll be pi d squared over 4. In most engineering applications, the diameter is given more than the radius, so pi d squared over 4 is a more convenient formula for calculating area. All right, so just hold on to that for a second. Let's look at our formula for mass density is mass over volume. We could rearrange this for mass and say mass is equal to density times volume. So if we wanted to calculate the mass of fluid in a container, we could say it's the density of fluid times the volume of the fluid, right? You'd have like kilograms per cubic meter times cubic meters is kilograms. Now we can write the volume of the container as being the area times the height. So we have mass is equal to rho times A times H. Let's put that aside for a second. All right, let's go down to pressure. Pressure we defined as force per unit area. Force is weight. That's weight per unit area. Weight is mass times acceleration due to gravity, mg over A. Now let's bring our formula for mass, and we'll put it here, rho AH. So that gives us rho times A times H is the mass, times G divided by A, and A, of course, will cancel in this case. So we wind up with pressure is equal to rho times G times H. Let me recolor that. Pressure is rho GH. That's called the pressure depth equation, and we'll use it a lot. If we happen to want to use weight density instead of mass density, that rho times G, recall, is the same as D. So pressure is D times H. We need to get some practice using this equation to get comfortable with the units, so that'll be our next exercise. Let's do this problem. Using the pressure depth equation, calculate the pressure exerted by a column of water 251 centimeters high. I'm going to calculate it in all the units we can. On a test, I'll give you this table of constant values. That would be the gravitational constant in units of weight per unit mass, and in terms of acceleration due to gravity, and the density of water in its various units. So we have P equals rho G H. We'll work first in the SI system, and the point of this is to get comfortable with these units. So I can say pressure, mass density in the SI system is 1,000 kilograms per cubic meter. The gravitational constant in the SI system, that's the weight per unit mass, is 9.807 newtons per kilogram. And we want the height in terms of meters. 251 centimeters is 2.51 meters. And that works out to be meters divided by cubic meters is per square meter. That's 24,600 newtons per square meter, which are pascals. Let's try the CGS system. Pressure. Rho is the mass density of water, which is 1 gram per cubic centimeter. The gravitational acceleration, that's like dynes per gram, force of attraction. Again, you can just look this up on the table, is 980.7 dynes per gram. And the height or the depth is 251 centimeters. This works out to be, we'll have dynes per square centimeter here, 246,000 dynes per square centimeter. I want to convert that to newtons per square meter. We've saw previously how to convert from dynes to newtons. There were 10 to the 5 dynes makes a newton. We want to convert from per square centimeter per square meter. We saw previously that
10 to the 4 square centimeters is equal to 1 square meter.
So basically we're dividing by 10. This becomes 24,600 newtons per square meter, or pascals. All right, one more time. Let's do it now in the British system. Rho GH, the mass density in the British system, the mass density of water is 1.9403 slugs per cubic foot. The gravitational acceleration, recall 32.17 feet per second squared, or as a gravitational constant, it's 32.17 pounds per slug. And we need to convert 2.51 meters to feet. So we had earlier that 1 meter is 3.28083 feet. You don't have to memorize that. That's 3.28083 feet per meter. This works out to be 9.55 meters. And that gives us a value of 514. Slugs cancel, that's pounds per square foot. Unit of pressure is force per unit area. Let's convert this to newtons per square meter. Right? So we'll cancel out pounds, go to newtons. You can check on page 50. There are 4.448 newtons per pound. I want to go from per square feet to per square meter. Okay, if we square this relationship, we'll have 1 square meter is 10.76 square feet. 10.76 square feet per square meter. Now if we work out our units here, looks like pounds are gone and square feet are gone, and we'll have newtons per square meter. And as expected, this works out to be 24,600 newtons per square meter. So there is the pressure at a depth of 2.51 meters of fresh water in the 3 different systems. Now it will behoove us to do it one more time. This time we're going to use the equation pressure equals D weight density times H, just to get familiar with the units. Again, we'll start with the SI system. Pressure is equal to, recall that D is equal to rho times G. So rho times G would be 1,000 times 9.807. Kilograms cancel, it would be 9807 newtons per cubic meter is the weight density of water. 9807 newtons per cubic meter times The depth is 2.51 meters, and as we saw before, that was 24,600 newtons per square meter. Let's do this again now in the CGS system. P is equal to D times H. Recall that D is rho times G. So here we have mass density of 1 gram per cubic centimeter, that's rho, times 980.7 dynes per gram. Grams cancel, we'll have 980.7 grams per cubic centimeter. We'll have 980.7 dynes per cubic centimeter times 251 centimeters. As we saw before, that's still going to be 246,000 dynes per square centimeter. And we converted that to 24,600 newtons per square meter. One more time, let's try the British system again. P is equal to D times H. D is equal to rho times G, 1.9403 slugs per cubic feet times 32.17 pounds per slug will give us pounds per cubic feet, and that works out to be 62.43 pounds per cubic feet is the weight density of water. We worked out that this was 9.55 feet. Wind up with 514 pounds per square foot, which we also converted back to 24,600 newtons per square meter. So let's just look at this again. Rho times G in the SI system, 1,000 kilograms per cubic meter times 9.807 newtons per kilogram works out to be 9,807 newtons per cubic meter as a weight density. 1 gram per cubic centimeter times 980.7 dynes per gram works out to be 980.7 dynes per cubic centimeter as a weight density. 1.9403 slugs per cubic foot times 32.17 pounds per slug works out to be 62.43 pounds per cubic foot as a weight density.
And that's enough for our first lesson on pressure.